Hello and welcome to our new unit on stoichiometry. The first thing we're going to discuss is the mole. Well, if I'm talking about the mole, why do I have a dozen roses, a dozen donuts, and a dozen eggs? Well, we know that 1 dozen equals exactly 12. Since we know that 1 dozen of anything is equal to 12, we can perform many calculations using that ratio. Let's begin with this very simple question. 60 donuts are how many dozen? Well, the first thing I'm going to do is I'm going to set up a ratio using the fact that 1 dozen of anything is equal to 12. In this case, donuts. I set up my ratio on the left-hand side of the equation. 1 dozen over 12 donuts is equal to, where did I get these numbers? They're directly from this equation. I was given 60 donuts and asked for how many dozen. So therefore, how many dozen is my unknown, and I put my 60 donuts on the bottom. Why did I do that? Because I want to keep my units the same. I've got donuts on the bottom and dozen on the top. Next, I'm going to cross multiply. That's why the arrows are there. When I cross multiply, I come up with 12x is equal to 60 times 1. Well, of course, we know that 1 times anything is just the number itself, so I'll simplify that 12x is equal to 60. How do I get that x by itself? Just harken back to your algebra class, and you know that you have to divide both sides by 12. When I do that, these 12s cancel out, and I'm left with x is equal to 60 divided by 12. Therefore, x is equal to 5 dozen donuts. 60 donuts is equal to 5 dozen donuts. Great. Let's move on to the next question. Okay, same thing. 1 dozen is equal to 12. How many donuts are in 11 dozen? I'm going to set up my ratio the exact same way. 1 dozen over 12 donuts is equal to 11 dozen over x donuts. Remember to keep your units in the exact same spot and you'll never go wrong. You simply cross multiply. 1x is equal to 12 times 11. Therefore, since 1x becomes x, 12 times 11 is 132. Your answer is 132 donuts. So you ask, what does this number have to do with chemistry? It's the exact same thing, but with a very different number. We call this number Avogadro's number. Wow, that's really, really big, isn't it? No worries, we're going to make it simple. This is Avogadro's number. That's a lot of zeros. However, we can shorten it. We in chemistry say Avogadro's number is 6.022 times 10 to the 23rd. You must commit this number to memory, as you will need to know it for the rest of the school year. So what does this number mean, and how does it relate to the donuts? Well, just like 1 dozen of anything is 12, 1 mole of anything is equal to 6.022 times 10 to the 23rd. The math seems daunting, but I promise you it's just as easy as counting the donuts. I love this picture at the bottom because it demonstrates what 1 mole of carbon atoms may look like. 1 mole of carbon atoms on the scale is exactly equal to 12 grams. Well, I probably shouldn't say exactly. We'll say roughly equal to 12 grams. Do you think you've seen that number before? Notice that the carbon here is black. Diamonds are not black, are they? So what element or substance do you think that is? If you said graphite, you would be correct. Okay. So if 1 mole of anything has exactly 6.022 times 10 to the 23rd particles per mole, let's go through some of the things we will encounter. A mole of carbon atoms contains 6.022 times 10 to the 23rd carbon atoms. That holds true for every single element on the periodic table. 1 mole of lithium is exactly 6.022 times 10 to the 23rd lithium atoms. We are just counting the number of items. Next, we're going to talk about molecules. Even though carbon dioxide is made of carbon and 2 oxygens, it doesn't matter. 1 mole of that molecule contains exactly 6.022 times 10 to the 23rd carbon dioxide molecules. The same is true for 1 mole of water and 1 mole of potassium chloride. Okay, here's the fun part. I would like you to pause your screen and grab your graphing calculators. I'll be here when you get back. As a matter of fact, I'm going to grab my graphing calculator. Here it is. The question: how many moles are 3.25 times 10 to the 20 atoms of, is that plumbum? Well, it is plumbum, but we call it lead. I am going to do this the exact same way that I figured out how many dozens of donuts that we had. However, I'm going to show you some tricks on the graphing calculator. As we go, I need you to pause and take notes, and perhaps write down this example so you have some way to do your work in class tomorrow. Here we go. Let's set up the ratio. If 1 mole of anything is equal to 6.022 times 10 to the 23rd, that's the ratio I use on the left-hand side. On the right-hand side, I use what was given to me in my word problem. They're asking me for moles, so that's my unknown. Keeping in mind that I keep it in the same spot where I had the moles here. 1 mole, X moles. That number, 3.25 times 10 to the 20, belongs on the bottom with Avogadro's number. Now, I did not put units here, and I should have, because they're asking me for the number of atoms, so I should have atoms here and atoms there. The next step is to cross multiply, just like we did before. We know we've got 1 times 3.25 times 10 to the 20 is equal to Avogadro's number times X. Well, I'm going to simplify now, because any number times 1 is itself. Uh-oh. I need to get X alone. What do? Well, same thing I did before. I'm going to divide both sides by Avogadro's number, and this actually will cancel out and leave X alone. Now we have to pull out the calculator and enter our numbers. I know that many of you are used to using the caret to enter exponents, but I'm going to show you a different way, and I would like you to use this way in class. It will avoid any confusion and any error. Let's turn my calculator on. Oh, let me clear that out. Okay. I'm going to say 3.25. And instead of writing times 10, I'm going to hit the second button and the comma. If you look behind the comma, there's 2 capital E's. That E actually means times 10. I do not need to use a caret here for my exponent. All I do is type in my exponent of 20. Great. That means 3.25 times 10 to the 20th. Now I'm going to divide it by Avogadro's number. For those of you that know how to do it, you should probably add Avogadro's number into your memory. Remember to use the E to the 23rd power. Enter. My answer is 5.39. Actually, I think I'm going to round that to 5.4 times 10 to the negative 4. Never ever forget to look to the right and write down times 10 and the exponent, because 5.4 and 5.4 times 10 to the negative 4 are very different numbers. Therefore, 3.25 times 10 to the 20 atoms of lead is equal to 5.4 times 10 to the negative 4 moles. All right. I hope you pause this, and I hope you write all of this down. Now we're going to try it another way. Here, I'm given the moles, and I have to figure out how many molecules. We're going to do the exact same thing that we did before. We're going to set up our ratio using what we know. 1 mole is equal to Avogadro's number. And on the right-hand side, we take what we're given in the equation, keeping in mind that you want to keep your units in the exact same spot. If moles are on the top here, they need to be on the top there. So 4 moles of water is equal to X molecules. Well, let's figure it out. I'm going to cross multiply, and I come up with actually X is equal to 2.4 times 10 to the 24. I simplified the 1 times X to get X, and I multiplied Avogadro's number times 4. Let's try that on our graphing calculator. Let me clear it. Here we go. 6.022 second, comma, which gives us our E, to the 23rd times 4. Enter. My answer, 2.4 times 10 to the 24. It's identical, isn't it? These 2 8s here I'm going to consider negligible and just use what I'm given. We like to keep this one whole number in front of the decimal point. I love this illustration because it's a great example of what a mole represents. If you look, we have a chemical equation right here, and we have the molecules and the formula units drawn out for us to visualize. So, here is an ionic compound. I know it's ionic. Why? NH4 is what again? Ammonium. So 1 mole of this ionic compound contains exactly Avogadro's number of formula units. That's what we say when it's an ionic compound. This compound decomposes into this ionic compound, which is also Avogadro's number of formula units, and it decomposes into this diatomic molecule. Since it's diatomic, instead of saying atoms, we use the word molecules. And then finally, we have water. Uh-oh. I see this number 4 here that I didn't see before. Well, that's okay, because what that number tells us is that we have 4 moles of water. We just calculated how to find out how many moles of water we have. So 4 moles of water is, oh, that number looks different than mine, doesn't it? Can you tell me why? They did not put their decimal point between the 2 and the 4. So what they did was they moved it over 1 to the right, and they removed 1 number from the exponent. Right here is a very important note. All of this time we've been working on chemical equations and balancing them. What those coefficients tell us are the number of moles of each compound and element that we have in a chemical formula. Okay. Here he is, the man, Amadeo Avogadro. He is the man by which the mole was named after. Very handsome fellow he is. Now, how do you think he had the time to figure out such things? Because he did not have the internet, an iPad, and an Xbox. Until next time.